Okay, typically the typical scenarios can be due to A, if we consider this is my capacitor, okay, so this is a device trying to pull down a capacitor, and this is a device trying to pull up a capacitor. Okay, now the typical scenarios are for an NMOS, okay, for an NMOS pulling down a capacitor, okay, so let us say that here V init is equal to VDD, okay, and here V init on the capacitor is equal to 0. Okay, and here V init for the capacitor is equal to 0. Now let us look at what would turn on the device to connect the output node to ground. Okay, on this side, what would turn on the device to connect the output node to ground is a pulse where the input of the PMOS device switches low, okay, and here is where the input of the NMOS device switches high. This will turn on the device and it will pull down the capacitor charge, so it will pull down the output, okay. Now the same for this scenario, what will turn on the device, the PMOS, is a signal that goes low, so the PMOS will be on, and here what will turn on the device is a signal that goes high, so that the NMOS will be on. Now the typical scenarios that we see, or the ideal scenarios, I will number the cases as case A, B, C, and D. Okay, the typical cases are case B, where an NMOS pulling down a node to 0. Okay, for this NMOS pulling down the node to 0, for case B, we have VGS will be equal to, at any time during the discharge, will be equal to VDD. Okay, so it can pull down, so the NMOS will pull down the node fully to 0. يعني V final for this will be equal to 0 for the capacitor. Okay, so this is for case B. Okay, this is for case B for the NMOS. Okay, and the second ideal case that we can handle is for the PMOS to pull up, because a PMOS is very good at pulling up, because if we inspect what is VGS for this, VSG for this PMOS, when the input has switched low, so for case number C, VSG is equal always to VDD minus 0, so it will be equal to VDD at the onset of switching and after switching, يعني during charge time, okay, and therefore since VSG is on, it's equal to VDD, it can pull up the output, so we will have V init equal to 0 and we will have V final will be equal to VDD for the PMOS. So this is for the NMOS case, for case B, and this is for the PMOS case C. Okay, so a PMOS pulling up, its source is at VDD, its gate is at 0, it will not be disturbed, it will be able to pull up the drain node all the way to VDD. The same here, an NMOS pulling down, its source is at 0, its gate is at VDD, and so it will be able to pull up the drain all the way to 0, fully to 0. So we have the V init for the capacitor VDD and the V final equal to 0. Okay, these are the typical scenarios or the typical cases that we have handled before. Okay. So therefore, given that V init equal VDD, if I rely on an NMOS to pull down the output, its VGS will always be VDD during this pull down. Okay, and therefore we will have a V final equal to 0. The same if I have a PMOS pulling up. Okay, so for the PMOS device, here, if we have a PMOS pulling up, okay, a node to VDD, okay, then its VSG will be during when the input switch is low, will always be VDD during the charging, and therefore we can reach all the way, it will always be on, and we can reach all the way to V final being VDD. Okay, so PMOS always on. Okay, now what happens if I use those devices the opposite way? What happens if I use a PMOS to discharge and an NMOS to charge? Okay, so what happens if I use a PMOS to discharge and an NMOS to charge? Now we have already seen before, the case where I have an NMOS device. Okay, so let us say that initially V init of the capacitor is equal to 0, and this is given. Okay, let me inspect Vs greater than Vt, so long that V out is less than VDD minus Vt. Okay, and this is where last time we said that if this is the output node, that V out or V cap will reach to the minimum, of Vg minus Vt and VDD. لأنه if I put a voltage here higher than VDD, then I can reach up to VDD, else I will stop at Vg minus Vt. فإذا an NMOS trying to pull up a node, the NMOS trying to pull up the capacitor will pull it up, may turn off, right? It is not very strong. So it is not a strong pull-up device, which is why in CMOS we typically use the NMOS for pull-up. هلا in a similar fashion, so لكن هيدي it is not the regular way of pulling up because we may reach to this value. Therefore, V init is equal to 0. Okay, so V init is equal to 0, but V out final will not reach VDD. So V out final will not reach VDD in this scenario. Okay, so let us look at the case of the PMOS pulling down. In a similar fashion, for the PMOS pulling down, it is not a good pull down. So assuming that given I have V init is equal to VDD in this case, okay, for the PMOS VSG, for the PMOS S is the higher, so this is the drain and this is the S for the PMOS, and this is the gate for the PMOS. So for the PMOS device, we have VSG is equal to its V out, right, minus 0. G during the activity, during when it's trying to be on, when the PMOS is on is when the gate is low, right? This is نحن هلا we talk about where we measure the delay. So the VSG is V out minus 0 because this is really the output node or the VCAP. Okay, and so it will be on so long that VSG is greater than magnitude of VTP, therefore so long that magnitude of V out is greater than VTP. Okay, so the output will start initially as function of time charged and it will discharge until it reaches VTP. لأنه beyond this point the PMOS will turn off. Afterwards the PMOS will be off. Okay, so the PMOS will be off and therefore the V final for the capacitor will be equal to magnitude of VTP in this scenario. Okay, so the V final will be equal to magnitude of VTP in this scenario, and the V initial will be equal to VDD, and the V final will be equal to magnitude of VTP. Therefore, the PMOS as a pull-up is a strong pull-up, and the NMOS as a pull-down is a strong pull-down, where V init equal VDD, V final will be 0. And the PMOS as a pull-down will be a weak pull-down. So if V init is VDD, V final will be VTP. And the NMOS as a pull-up will be a weak pull-up. Okay, so V out final will be probably VDD minus VT or the minimum of VG minus VT and VDD. Okay, so here if we are using the individual devices for pull up or pull down, given that nobody is creating a contention with them. And when we will study those cases, we will study them independently. If we are studying the different types of inverters, we will be studying the PMOS and the NMOS in the regular places where the PMOS is being used as a pull-up or the NMOS being used as a pull-down. We had a few scenarios where we saw the NMOS or the PMOS being used for where we saw the NMOS basically being used for pull-up. بس هلا عم نحكي عن individual devices. So this is related to the individual devices, assuming the capacitor is initially pre-charged to this value. Okay, so now if we switch to the example that has been provided in the home in the problem solving. For this example that has been provided in the problem solving, we are being given a certain technology with a specific L اللي هي شوي أقل من the critical dimension. We are being given VDD, VT, COX, gamma, lambda, and mobility, VDV set, and the 2 هلا بهالproblem, in this problem, we are given a PMOS device with a specific width, and we are being told that PMOS is discharging the capacitor of 50 femtofarad, and that assuming that the capacitor is initially charged to VDD. So here I have V init equals VDD, and they're telling me to ignore body effect, and he's saying that a step function, that Vn, a step function, is applied. Okay, at the input. So it is high to low. So Vn becomes low or 0 during to activate the PMOS when I'm trying to discharge this capacitor. So what is the final value at node Vx? We said that this is G and this is Vx, and we said that VSG is going to be greater than VTP, but Vs is Vx minus Vg, which is 0, is greater than VTP. So magnitude of VTP. And now we look at the condition to turn the PMOS on. And then in the second question, they asked me to determine the 50% delay, and we need to find for this the current at the onset of discharge T1 and when the output reaches its 50% point. So if we want to look at point T1, so this is the transistor. Okay, this is Vx. Okay, it's a PMOS. The input has switched to 0. Okay, so we said that the point T1 typically is at the onset of the switch, yani the input has already switched to 0. And point T2 is the point at which the output or Vx with time, T, okay, this is Vx is initially VDD by another means, by another path. This is not that it might be being pulled out through another circuit. And when this transistor is initially off, when this transistor turns on, okay, at time T1, okay, Vx is going to start to be pulled down. Its final value will be VTP. But the 50% time point is the time point T2, and at T2, V out or Vx reaches its 50% value, which is the midpoint between its high and low, which is Vx will be equal to VDD plus VTP over 2. Okay, so therefore at time point 1, at T1, Vn is equal to 0 and Vx is equal to VDD, and at T2, Vn is 0, the PMOS is still active, and Vx is the 50% value, which is VDD plus magnitude of VTP over 2. Okay, فإذا we fill this information, so Vn equal Vg equals 0, and Vs is equal to Vx. Initially, it's the initial value, and then it's VDD plus VTP over 2. The drain of the PMOS, this is the drain of the PMOS, it is always 0. Okay. Later, we will learn about the average capacitor current. Okay, we don't need to worry about this quantity, but if we want to calculate the current that is flowing in the capacitor, so IC at T1 will be equal, whatever current is flowing in it is the current that is flowing in the PMOS, so it's equal to minus I of the PMOS. Okay, so we derive it from IP of the PMOS, okay, and to derive IP of the PMOS at T1, okay, we need to really look at VSG, VSD, okay, we'll say that VSG is equal to VDD minus 0, so it is equal to VDD, and VSD is equal also VDD minus 0, so it's equal to VDD, and we can derive the unified current model equations. Okay, the same for to derive the capacitor current at T2, we need to derive the transistor current at T2. For us, we can derive from the transistor current at any time point the resistance, which will be really VSD or Vx over I. And for the PMOS, we will have at this point, Vn is still equal to 0. So VSG will be equal to, but the V out is VTP plus VDD over 2 minus 0. So VSG will be equal to really Vs, which is VDD plus magnitude of VTP over 2 minus 0, and VSD will be equal to VDD plus magnitude of VTP over 2 minus 0 also because VD equals to 0. And now from those quantities, we can determine the three quantities of VSG, VNCT, VD, VSAT, and VSD, and find what region it is operating in, and therefore define the current that is flowing in the transistor at this specific time. Okay? So now in problem number 2, we are given a circuit with two transistors where transistor T1 drives the PMOS transistor T2. A step input is applied here at Vn, okay, and the gate of input T1 is connected to VDD, and هيدا is always on as a PMOS, okay, as an NMOS, pardon me. And he's telling me the values of the capacitors, and he's telling me that VDD equals to 2.5. The output of the circuit is V out, which is here, and we're being asked to use the unified current model to derive the parameters to derive the current flowing in the different cylinders. Okay. So the first thing we're being asked is that before Vn switches to VDD. So in the first scenario, first he's telling me that before it switches, if Vn is equal to 0, label the source and the drain nodes of T1 and determine the initial voltages Vg and Vout. Okay, so if Vn is 0, okay, let us see first, look at transistor T1. Transistor T1 is independent of the input. It is always on. This is 0. This is an NMOS, okay, pulling down an internal node. Okay, so it is pulling down an internal node to ground. Okay, so ideally speaking, based on the rules that we have seen, an NMOS that is on, okay, which is this node ground and this node, so it is on, therefore it can pull down this node G all the way to 0. Since this has been there for a long time, since I'm solving the initial condition as a DC problem, okay, I know that node G will be initially 0. If we tell you that assume that the capacitors are initially discharged, okay, this means that this voltage will be 0, this voltage will be 0, okay, this device is on, this is 0, this transistor is on, okay, and this is initially 0. Okay, now if I have a transistor where the source and the drain are both 0, so if I have a transistor where the source and the drain are both 0, then we don't know which one, so we can arbitrarily state that this is the source, which is grounded, and here for this we can say that this is the source because it is the supply that is going to flip to high later. What matters, assuming that we told you that assume that the capacitors are initially discharged, now that Vn makes a sharp rise from 0 to VDD, label the source and the drain of T1 and T2 after the transition when Vn becomes VDD. Okay, so when Vn becomes VDD, the higher is the source. Okay, this was initially 0, so this is the drain that we are trying to charge. And for the NMOS, it is not going to be affected, but we will assume that the ground is the source because it is the lowest. Okay, so we will label them. And then they ask me, does the voltage VG across C1 change? No, it is not going to change because this device is always on and it is really an NMOS pulling down a node to 0. So it is not really affected by the path of the PMOS. Okay, there is nothing to connect VG to the source and the drain of the PMOS. Here I only see a capacitor. I don't see. I see a loaded capacitor لأنه الكرنت هون هو زيرو. اوكي بس بشوف الكاباسيتيف لود لهيدا الترانزستور I don't see any Z يعني I don't see any resistance or impedance. اوكي طب so لكن G is not affected. Continuing part B, in what direction does the output V out switch? Okay, so in what direction does the output V out switch? Okay, so here what I have a PMOS transistor whose gate is 0, it does not change, and the PMOS transistor now all of a sudden has a supply voltage which at time T1 has a switch to VDD. يعني أنا عم بشغل هاي ل VDD, and here okay I have a PMOS which has now VDD on one side and it has an output capacitance that was initially 0. Okay, so let us label the nodes for this transistor. The nodes for this transistor is S because it is the higher voltage, and this would qualify as D. And for this PMOS T2, what I have is that I have Vs equal to VDD, Vg is equal to 0 and it is controlled by the upper transistor, and I have Vd or Vout. Vd is equal to Vout, and now it will be charged because the PMOS is on. The PMOS is on, and what happens is that at time T1, okay, Vs for the PMOS moved from 0 to VDD, okay, and so at time T1, and what is going to happen to the output? This is exactly equivalent to the problem where I'm trying to charge the output. So it is going to try to charge node Vout through the PMOS. The only difference here is as follows. The only difference here is as follows. Before, we used to say that the source is high, but the gate turns on. Okay, so traditionally, we used to say that I have a PMOS where the source node is at VDD and the gate turns on, and the gate becomes low. Okay, and so what this means is that the PMOS will be on as function of Vg, right? So this is Vg, used to be high and it turned to low, and accordingly, once the PMOS turns on, Vx or Vout is going to charge up, assuming that Vx init is equal to 0. Here, what is happening is that I have a PMOS, doesn't matter how it looks like, its gate is 0, okay? It was forced or connected to a forced signal that was originally 0 and then rose up to VDD, so this is its source node, and its drain had Vx init equal to 0, okay? So what happens to this transistor, let us label 3 time points here, T0, okay, here T1 at the onset of switch and time point 2. And so if I draw Vs of t as function of time, I will have here T0, okay, I will have here T1 at the onset of switching, and then I will have T2 here at 50% delay. And so let us look at the transistor state. Okay, so at T0, I have Vs equals 0, Vg equals 0, and therefore Vsg is less than magnitude of VTP, and so the PMOS will be off. And then at T1, I have now Vs equal VDD, Vg equal 0. So the PMOS will be on. Now and it will start to charge the output. It will start to charge node X to VDD, okay? Because now the source is at VDD, okay? So from this point and on, the transistor is really like a PMOS whose gate is at 0, whose source is at VDD, and it's starting to charge a capacitor where the output node, okay, where the output node was initially 0, okay, and then it is going to charge up. So this is at T0, this is at T1, and then it is going to charge up at T2. Okay, so let us see for this transistor what are the characteristics. So at T1, Vs is equal to VDD, Vg equals 0. So the PMOS is on. Okay, let me draw the transistor now. I have this S, G, and X. And we know that Vx is equal to, at T1, we know that Vx was equal to 0. Okay, therefore at T1, VSD is equal to really VDD minus 0 equals to VDD. Okay, now what would be the final state for this transistor? The final value for this transistor, V final for this capacitor, V final X, let us see. So the PMOS with a step function at the source will have Vs at VDD, okay, and Vg at 0, right? And it's trying to pull up this node. So Vsg, when Vn equals to VDD, will always be is equal to VDD minus 0 and will be greater than VTP. So in this scenario, for my PMOS, where I have applied here a step function Vn at S that rose to VDD, okay? Okay, if it remains like this forever, for infinity, then the PMOS will be always on because Vsg is equal to VDD minus 0, and therefore it can pull up Vx to VDD. Okay, فإذا هون it's acting as a pull up. Now, since I know that V final is equal to VDD, then I can calculate at T2. Okay, I know that Vn, which is Vs, will be VDD. And I know therefore that Vsg will be equal to VDD minus 0 will be equal to VDD. And then Vx would have reached its midpoint, which is V final plus V initial, okay, over 2, which is equal to VDD over 2. Okay, therefore VSD is equal to VDD minus VDD over 2, which is VDD over 2. So now I have my VSG and my VSD at the different time points. Okay, and now I can go back to the circuit here and I can answer. Okay, continuing, in what direction does the output switch? The output is going to be pulled up. Okay, so here it is drawn, يعني رسمينا نحن in a different direction. So here, let me draw it for you. What is happening is that I have the PMOS. The PMOS is drawn in this direction. Okay, it has a 0 here. It has a signal that is going up here. And therefore, it is really equivalent to a problem at T1 where this is VDD and it's trying to pull up the node that was initially 0. Okay, so it's trying to pull up the node that was initially 0. And هيدي السورس, هيدي drain, and we can draw it in a different way. Let us draw it the way we conventionally see it. The higher node is on top. So what happens here to the circuit is that this is T2, okay, this is Vx, okay, and here this is always 0, this is the PMOS, and now S after T1 it is really VDD. Okay, between T1 until the end. Okay, لأن هيدا هو step function. This is S. So the final value for Vx is going to be VDD in this scenario لأنه throughout VSG is greater than VTP. So it will pull this node up to VDD. Great. هلا determine the final voltage at the output. We determined it. Determine the propagation delay. هلا نحن we are not going to use the average current method. We are only going to find I of T1 and I of T2. Okay, so we are only going to find I of T1 and I of T2. We build a table. At point T1, Vg equals 0 and the same at point T2. At point T1 and T2, Vs has flipped to VDD. At point T1, Vd was Vout equal to 0. And at point T2, Vd is going to be equal to Vout, which is equal to VDD over 2. And now we can calculate from it VSD and VSG and perform the current values for at time point T1 and at time point T2 as you see here. Okay, thank you.